Okay, waiting to start the recording. Okay, I had some troubles with the laptop overheating. Sorry about that. But also I was trying to get this proof right. So that we assume two ingredients. One ingredient is that we do all this stuff carefully enough, and then we just show that in a small interval, it doesn't really matter how much those variations change. We just bounded by the supremum over the derivative, and that's fine. So this is more or less some sort of stability because it's a linear differential equation. So that's what I was trying to derive. And you derive it one way or another. What's important? What's important is that that we have this epsilon squared scaling here. Yeah, maybe I need to pick up a few constants here or there, but basically we have this bound where we can include those added constants. We can include this in H prime ultimately, and we will have some constant that depends on this H prime, and then we are almost done. Then the final thing is that we have our interval from 0 until 1, and we have those equidistant times t and minus 1. Okay, and basically because it's a linear equation, we have those propagation times u if this is tk and this is tk plus 1, then from tk to tk plus 1 I go with u tk going to tk plus 1. So my full continuous evolution, in the sense that the evolution, which is the solution to the time-dependent Hamiltonian, is just the composition of evolving through those steps, and they could seamlessly combine with each other. That's not a problem. And then we have minus e delta t h t0 e to I delta t h t1 dot e to I delta minus I delta t h t n minus 1 in this case, because I start on the left edge. Doesn't really matter in this case. So now I need to do telescoping. So depending where I start. So I could start with the last one, and what do I add? I repeat the same thing. So I would be adding this term, and then I would, okay. So let's write it out. T0, T1 times U T1 T2 dot U Tn minus 1 Tn, and then I do minus T0 T1 dot U Tn minus 2 until Tn minus 1 times, and now I change by saying delta T h Tn minus 2, always in the beginning of the interval, plus u t0 until t1 dot u Tn minus 2. This is mundane, but this is really what it costs to do the proof. E delta t h Tn minus 2, and then here I have minus e delta t h t0 dot e to minus I delta t h Tn minus 2 times e to minus I delta t h Tn minus 1, and the norm closed here. But if we take an upper bound, I can insert the triangle inequality here. And then we use norm invariance. So norm invariance was that u a minus b is what? It's actually, in our case, for the operator norm, it's equal to the norm of a minus b. So now you see that I can, in this case, I can factor out, what can I factor out? I can factor out the beginning. So I drop this, which means that from here I get my bound u Tn minus 1 comma Tn, that's our propagation in the last segment, minus e to I delta th Tn minus 1 plus, and here I can factor out this part, so I get this with n minus 1, so replacing n by n minus 1. And then we were discussing this quite a lot for Trotter Suzuki. You just keep iterating this this kind of telescoping recurrence, and it means that I will have the bound of summing over k from 1 until n, and then I will have u t k minus 1 comma t k norm minus e delta t h t k minus 1. Right? But now what I get is n times delta t squared times our h prime constant in each interval, but we have uniform constant over the entire possible time duration, right? And delta t is the total time duration divided by n. So what do we get? We get t squared divided by n h prime. And okay, I survived this proof. Some proofs you have to survive. It gets complicated a bit, right? But they only so the last part is something that we should be familiar with already. So I will talk about this a little bit more. So if I have a sequence of unitary operations u1 until un, and I have another sequence v1 until vn, then I can bound this by always inserting u1 until un like this. And then I can do, for example, plus or minus u1 until un minus 1. And here I switch un with vn, right? And I added, so I subtracted, so I need to add it again. So I'm adding exactly the same thing, n minus 1, vn, and now I have v1 until vn norm here. So triangle inequality, insert here, and then you see what you're factoring out. Here I should have un minus 1, so I can factor out this, and then I can forget that, right? Then I use norm invariance, and wow, I have un minus vn. Okay, and then I factor out vn, remove this, so I have v1 until vn minus 1. So it's smaller. At some point I will have v1 v2 minus u1 u2, right? So now this one will be easy. So dot 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 dot, right? And so let's do this one. V1 minus v2. Let me add minus v1 u2 plus v1 u2, right? So this one goes with this one, and this one goes with this one. So using triangular inequality, we get v1 v2 minus v1 u2 plus u1 u2 with there was a minus here, sorry, plus v1 u2. So you see what we can factor out in the last step of this induction. You can factor out those two, right? So if n would be equals to 2, it would be really v1 minus u1 plus what do we have? u2 minus v2, right? And instead what we are getting is that this kind of product, this product here, so we get u1 until un minus v1 until vn is smaller or equal the summation uk minus vk. So this is something that should be in your repertoire. If you have those products, and then you kind of use this triangle inequality by inserting this identity term, this this zero term, additive identity, yes? And then you switch the product into the summation, okay? So we did exactly that. And basically for us today, UK was the smooth evolution from TK, let's say, to TK plus 1, while VK was the piecewise constant evolution, just a short time evolution with the Hamiltonian TK, right? And because TK and TK plus 1 and so on is small, we were using this kind of perturbative bound here, just expanding it out and making sure that the Hamiltonian doesn't differ too much, okay? So this step is very safe. That's why I was saying it matters what happens on the small interval. And then the only thing that I was kind of a bit messy about was where do I Taylor expand, and is this a correct Taylor expansion, in which step you do. And I kind of surprised myself that I had two terms. One, actually the Lagrange term was naturally giving us the epsilon squared h prime. And then we had here this kind of supremum. And so we would need to still use one more time the Taylor expansion to get it right, maybe, for a time-dependent Hamiltonian here. Yeah? So this is using this kind of continuity all over the place. So we are assuming that HT is actually a smoothly varying time dependence. Okay? And in this case, what we showed is that that basically we are writing those operators for this unitary concatenation. So where did we have it? I was kind of writing it out more or less somewhere, right? So T1 until T2, T2 until T1, where this is all easy. And then we had the Trotter-Suzuki decomposition, and that way we have proven that those piecewise constant approximations, what I was talking about geometrically here, that this is actually approximating it at some point. Geometrically, you see that this is a smooth curve. So if HT is varying smoothly, then we have a smooth curve. If we have a smooth curve, then of course a smooth curve, we should be able to approximate by piecewise constant geodesics, just making sure that geodesic is then tangential to that point. That's what we were doing today. Yeah. This relates to the Trotter-Suzuki decomposition. This is more or less the same as Trotter-Suzuki decomposition. It's just we had this perturbation bounds in the small TK plus 1 interval. Yeah, that's the only difference. Okay, let me put this. So when T goes from 0 until T, then this full integrated evolution gives rise to an operator. And sometimes we write it like this. This is just symbolic, indicating that HT, the generator, was varying from 0 to 1. And actually, this operator can be defined that way. Yeah, it can be defined more or less constructively here, where this more or less Trotter-Suzuki decomposition. This is not much different. Okay, and that's why it's called Trotter expansion, because Trotter was a mathematician who considered those kind of. It's actually called Lie Trotter-Suzuki decomposition. So Lie groups is the unitary group, and Lie was already looking at this kind of stuff. Okay, so two ingredients. Make sure that locally this is fine, and then make sure that your telescoping and those kind of iterated bounds are fine. So I was proving this quickly because I don't want to extend too much. And where this was going wrong was that we were seeing those recursions all the time, and if you would be pushing it through, it would be a bad bound, but I won't. That wasn't actually, the complication wasn't intended, but it's actually a good lesson. So the trouble that I was having here today is actually that those bounds are blowing up, because I was saying I was trying to bound at some point psi2 from psi1, and I get psi1, psi2 in some other point in time. So it's very like self-repeating. This recursion is quite bad. And when something like this shows up, you can still bound it, but the bound will be very, very bad. So we got a really good bound. But when you get a function, let's say I have a function g of t. Let me consider a function g of t is norm psi t minus some other psi t. And if I show that the derivative of g of t is bounded by g of t, then what you consider is kind of an upper envelope of that equation. So you consider this equation, h of t is equals h of t. And we more or less know what happens. It will be an exponential, right? So h of t will be in some way an exponential e to power t, and that becomes a very bad bound in the total duration. Okay, so I was having troubles because I couldn't find in my notes the step that exactly circumvents this. And at some point you might get an issue that you will have a bound which is recursive in this way. And then you more or less should know that it means that the upper bound is actually scaling exponentially in our time duration. What we got is actually something much stronger. So this was telescoping, this just general. We got something polynomial in the time duration. Much better scaling, not exponential, polynomial. Okay, and the step where this happens is thanks to hopefully correctly deriving that on a whatever small interval, we can do those kind of suprema. So the supremum over a smaller interval of this finite difference quotient, more or less, can be upper bounded by inserting here the Taylor expansion with the Lagrange term. If today this was a bit fast, then this is just standard matrix analysis, that this is a continuous function in higher dimensions. And basically there's this notion of taking those derivatives. So this equation is really not that far away from what I was writing here. Okay, that's more or less something that I was just using on the go. But once you have this, I'm pretty sure that you could really make airtight the proof that I gave here. This is a lot of transitions, I understand, but somehow I didn't manage to do it faster today. Right? So changing into integrals. So if I want to check how do solutions differ, I can insert an integral and integrate out how their differential equation differs, right? This is just fundamental theorem of algebra in some way. But once I have the, using this fundamental theorem of algebra, once I have the derivative, I get my difference of those Hamiltonians. Once I have this difference of the Hamiltonian, it's like goes and goes, and we're more or less done. And once we were happy with the bound being of the type on whatever interval of length epsilon squared, once we have this O epsilon squared, we insert that in telescoping and then you're done. I mean, as soon as you have that, then the telescoping is generic. A very good exercise to see that you can exchange products into summation of those differences. And I refer to this broadly as telescoping because those differences just come together, right? So the longer this product, the longer this sum here, because more of those insertions. And I was doing this point by point, but you could use induction to just postulate the formula and then just go, right? So this is a very generic tool, telescoping in those bounds. Yeah, and my logic here was chop it into small intervals. On small intervals, I will be at home, I will just use telescoping. So I just need to make sure that I don't mess up all those Taylor expansions in this case. I had to improvise a bit because this didn't work the way I had it in my notes. And then on small intervals, I get this, right? So telescoping is actually quite fast. Reduce it to something local and then make sure locally it doesn't differ too much. And then you kind of bound it, okay? So that way we derive this error bound. Okay.